John Rees, and I'm a resident astronomer here at Lick Observatory. So here at Lick Observatory, we're about an hour outside of San Jose on top of Mount Hamilton. We're at an elevation of 4,200 feet, or about 1,300 meters, which is relatively low in terms of modern astronomical observatories, but of course we were the first permanently occupied mountaintop observatory. Behind me you can see all of the telescopes that we have on site here. So directly behind me here we have the Katzmann Automated Imaging Telescope, or the KATE. Then in the background there we have the largest telescope on the mountain, the 3-meter or 120-inch Shane telescope. Behind that we have the dual astrograph, and then we have the dome for the automated planet finder, the 2.4-meter newest telescope on the mountain. And then right in the background we have the large dome housing the 36-inch Great Lick Refractor, adjoining the visitor center and the nickel, the 1-meter nickel telescope.
I'm Paul Lynham. I'm a resident astronomer at Lick Observatory. So the story of Lick Observatory doesn't start here in California. It starts on the other side of the country, in Pennsylvania. As a young man, James Lick grew up in Pennsylvania, and he learned woodcraft from his father as an apprentice. In his late teens or early 20s, he left town to go and seek his fortune, and he wound up making piano cases, eventually in South America. Later in life, in the 1840s, he was watching the political situation and the war with the United States and Mexico, and he decided to liquidate the value of his piano-making business in South America and come to California. In 1848, he landed in Yerba Buena and declared 3 items at the customs house: $30,000 of Peruvian gold doubloons, a workbench and tools for making piano cases, and 600 pounds of chocolate from a friend, Domenico, in South America. He went into the town and bought a solid building to place his treasure in, and that could have been the end of the story. But something happened 2 weeks after James Lick's arrival in Yerba Buena, which was to become San Francisco, which was to change California, the world, and astronomy forever. Gold was discovered in Sutter's Mill in Coloma. James Lick bought and sold land while people were going prospecting for gold, and he profited. In later life, James Lick suffered a stroke, and he started to consider his mortality and the disposal of his wealth. So in 1875, he designated the summit of Mount Hamilton to become the future location of his observatory and mausoleum. James Lick passed away in October of 1876, where the project to build the observatory, the first purpose-built observatory for astronomical observations placed at altitude, got underway. The project took some 10 or 11 years to complete, and the observatory opened in January of 1888. The centerpiece of the 1880 observatory was the Great Lick 36-inch refractor, and in the years subsequent, the observatory became the center point of world observational astronomy, adding to its inventory of facilities both on Mount Hamilton and around the world. For the first several decades of the 20th century, Lick Observatory was the most important observatory in the world.
I'm Eleanor Gates. I am a staff astronomer here at Lick Observatory. I'm standing in front of the 36-inch refractor. This is the telescope that James Lick gave $700,000 of his fortune to construct to be the greatest telescope in the world. The telescope itself is about 58 feet long. At the top end are 2 36-inch diameter lenses spaced about 4 inches apart, and then the light goes through the tube down to the eyepiece, and that is where you look. So today we use a very tall ladder to get up to the eyepiece to take a look through the telescope. But back in the 1880s and until very recently, this floor I'm standing on is actually an enormous elevator that you could ride up to get to the eyepiece and view all night long. And then as the telescope moved, as say the lens end moved up while you were observing, the floor could be moved down so that you could keep comfortably looking through the eyepiece, or taking long exposure photographic plates, because in the original days of this observatory, the original few decades, it was used with photographic plates as well as an eyepiece to take data. Now the telescope itself is mounted in the middle, so you'll see some gears up there that allow the telescope to move in a pure east-west or north-south direction, depending on which gears you're turning. And you'll also see some ship's wheels up there, and that is how the astronomers would move the telescope. The telescope itself weighs about 14 tons, and that's a lot of mass, but it's very carefully balanced so that you could just use those big ship's wheels up there, turn them to move the telescope to wherever you needed to look on the sky. So we're here in front of James Lick's tomb. James Lick provided the funds for building the greatest telescope in the world back in the 1880s, but he didn't live to see the construction of his monument. He died in 1876 and was originally buried in the Masonic Cemetery in San Francisco. In 1887, as they were getting ready to do the final installation of the telescope, they disinterred James Lick from San Francisco and reinterred him here at Lick Observatory. And so he really is here behind this plaque. And I think he'd be very proud of the work that Lick Observatory has done and the great discoveries that his monument has participated in. The dome behind me is actually the oldest permanent structure on top of Mount Hamilton at Lick Observatory. The dome itself began construction in 1880 and was completed in 1882, and its original telescope was a 12-inch Clark refracting telescope. In fact, that telescope had a very early noble visitor, King Kalakaua from Hawaii, came to Lick Observatory in 1881, and they weren't done constructing the dome or the telescope, but they hurriedly erected the telescope, set it up so they could show King Kalakaua the wonders of the universe, and then, once he left the observatory, they packed it up and finished construction of the dome, and it was completed in 1882. And then they started doing astronomical research before the main observatory opened in 1888. The dome today houses the 1-meter nickel telescope. This is a fully modern telescope that is computer controlled that was installed in the 1970s because the 12-inch Clark refractor that was installed in the dome originally was just too small to be competitive for modern astronomical research purposes. The telescope uses a mirror to collect the light that's 1 meter or 40 inches in diameter. So they can point the telescope wherever they want to in the sky. The dome slit will open up and the telescope dome can rotate 360 degrees, so point any direction, so that you can observe any object in the sky you wish. The nickel telescope is used for a lot of different research programs. One of the primary programs it's used for today is following up supernova explosions. Supernovae are stars in other galaxies that explode. There are two different main types. One type is the type 1A supernova, where you have a white dwarf star that has a companion star that is expanded into a red giant and is dumping material onto the white dwarf star. When that mass of the white dwarf star hits 1.4 times the mass of our sun, it goes kaboom, blows itself up, and these explosions are visible all across the universe, so you can see them at great distance. So the other type of supernova is the kind of type 2 supernova, where you have a massive star, much more massive than our sun, At the end of its lifetime, it becomes a red giant star, then they become unstable, and then it goes kaboom and blows itself to bits in a supernova explosion. So these are very similar. When all of a sudden you see this bright new star in another galaxy, and our students are actually measuring its brightness and how it fades over time. So that's using what's called a direct imaging camera on the telescope. And of course, you can use it to observe not just supernovae, but also you can use it to observe asteroids, galaxies, pretty much anything in the nighttime sky. We have other instruments you can put on the telescope, such as the NIRO SETI, the Near Infrared and Optical Search for Extraterrestrial Intelligence. And this is an exciting instrument we have on the telescope. They look at stars like our sun that might have planets around them, and then they're searching for laser signals that are coming from that civilization that might be there, and we might be able to eavesdrop on them by seeing their laser signal. Now, the signal probably won't be strong enough for us to understand the message or do that, but just knowing that there's a intelligent life form made signal coming from another star system would be a huge discovery. And so that's another type of research we're doing on the nickel telescope.
Ever since its opening in 1888, Lick Observatory has been innovative in exploring astronomical technology. One example is the arrival on the mountain of the first glass reflecting telescope. It's called the Crosley telescope. This telescope arrived on the mountain in 1895, and soon after its deployment was used in combining photography with astronomy to explore the then called spiral nebulae, which were later determined by Edwin Hubble and co-workers to be island universes, galaxies beyond our own Milky Way. As the new technology glass reflecting telescope, the Crosley telescope, went into operation in the early 1900s at Lick Observatory, it led the way in astronomical technology. Most astronomical reflecting telescopes in the world owe their heritage to the Crosley telescope and the standards it set and the techniques deployed here at the mountain. For 50 years in the early 1900s, Lick Observatory held the workhorse of California astronomy in the object of the Crosley telescope.
Okay. So we're standing here in front of the newest telescope at Lick Observatory. This is the Automated Planet Finder, or APF, and this is a 2.4 meter robotic telescope. So you may notice that the dome here is a lot smaller than some of the other telescopes you'll see on the mountain, and that's because it's a very modern design and fully automated, so we don't need people inside the dome. The telescope actually moves entirely autonomously, and each night the telescope itself will check the weather at the weather stations we have on the mountain, decide whether conditions are safe to open up and observe, and then we'll go off and observe from a list of targets that the telescope has. So we don't need any operator intervention. This telescope can do its science 365 days a year without any telescope operator. The telescope itself is designed to look for exoplanets, so planets around stars other than our own sun. And so to do this, it has a very high precision spectrometer, and so it takes the light from, it'll observe stars, take the light, split it into a spectrum, much like you get when you pass light through a prism. It'll split it into its component colors, and by looking at that light for signs of known shifts, you can look for signs of a planet orbiting around a star. And so to do this, you really need many observations of a star over a long period of time, which means a robotic telescope like this is absolutely perfect, because it can go look at a star for many nights over the course of months or even years to look for evidence of these planets.
The Carnegie Dual Astrograph is one of our historic telescopes. It's actually two telescopes mounted on the same pier that are 20 inches in diameter, so that both telescopes look at the same object at the same time. One of the telescopes is designed to focus the blue light. The other one focuses the yellow light. So the astronomers would put photographic plates at the focus of each telescope and get pictures in two colors at the exact same time. So the question is, why would they go through the trouble of taking two pictures in different colors at the same time? Well, it was really two reasons. One is by looking at two different colors, you can measure the temperature of your star. And so they surveyed the entire sky visible from Lick Observatory and measured the physical properties of all the stars they could identify. But the real reason they did this was actually a much more difficult measurement, just to measure how the stars were moving. So they were very accurately measuring the positions of each and every star that they identified and comparing their positions to the background galaxies. And so they measured millions of star positions, and they did it in two colors because they wanted to measure the true position of the star. And the Earth's atmosphere acts like a prism. Much like a prism will take white sunlight and make a rainbow, our atmosphere bends the light of the blue light differently than the yellow light. But if you take the exposures at the exact same time, you can actually work backwards and remove the Earth's atmosphere and its effects on the light, so that they can measure very precisely the positions of each one of these stars. After they measured all these positions, they waited about 10 years, and then they took photos of the entire sky again, and they compared the same stars and saw how their positions had moved over the intervening decade or two. And this was the first time that they were actually able to measure with great accuracy what's called the proper motion of all the stars in our galaxy. They combined that with radial velocity, that's the velocity of how fast something's coming towards or away from us, from the 36-inch refracting telescope, and we're able to very accurately measure the absolute motions of these stars in our galaxies and how the stars are moving in the spiral arms and orbiting around the galaxy, as well as with respect to each other in our local region of the galaxy. So this was called the Lick Proper Motion Survey and was very, very important scientific result. And is still used today for calibrating modern telescopes we put in space, like Gaia, to measure the positions of stars. However, that telescope is no longer used today, but that doesn't mean the dome behind me is no longer used. We have just earlier this year installed a new instrument called PanoSETI, which is searching for laser signals from intelligent extraterrestrial life. And so these are cameras that look at large portions of the sky and looking for those laser signals as the star drifts by its view. And it's a test program, but it's been very successful so far. Everything appears to be working. So ultimately, they plan to have cameras that view the entire sky all the time and deploy many of them around the world so they can search for intelligent life out there in the universe.
Behind me we have the enclosure of the Shane telescope, or the 3-metre telescope, or the 120-inch telescope. This telescope went into operation in 1959, and at the time it was the second largest telescope in the world operating at that time. It was second only to the Palomar telescope down in Southern California, and it turns out to be a very close relative of that Palomar telescope. When they were experimenting with the technology to build the Palomar telescope in the 1940s, they were experimenting with new materials in Corning in New York to try and construct a piece of glass or a piece of fused quartz that was 5 meters across and could hold its own shape. So in the process of experimenting, they created test pieces, and eventually they worked their way through a disc that was 40 inches across and 80 inches across and so on, all the way up to the Palomar 5-meter diameter. One of the pieces of glass that was surplus to requirements after that project was the 120-inch diameter piece of glass, which was eventually bought and shipped here to Mount Hamilton. The building was constructed, and inside the building we assembled the Shane telescope. This telescope is a very versatile telescope. In contrast to some of the other more modern telescopes we have here on the mountain and around the world, which are automatic or robotic and dedicated to particular types of investigation, like exoplanets or supernovae, this telescope has a large inventory of equipment and instruments and cameras on board, which allows us to address virtually any astronomical topic.
The Shane telescope is the largest telescope on Mount Hamilton. It was built in the 1950s and used for the first time in 1959. The telescope is 3 meters or 120 inches in diameter. And the mirror for the telescope sits in this yellow cell behind me at about eye level. And the telescope collects light by pointing the telescope wherever you want it to go in the sky. And there are 2 axes of motion for the telescope. There's a pure east-west motion, which allows the whole brown fork that supports the telescope to rotate. And then there's gears at the top of those brown tines that allow the telescope to tip in a pure north-south direction. So you point the telescope wherever you want it to be, and then the light will come down the tube, hit the mirror at the bottom of the telescope, go up and hit the secondary mirror at the top, and then come back down and go through an 8-inch diameter hole in the middle of the primary mirror to the instrument sitting at the bottom of the telescope. Now, this telescope is designed to be multifunctional, to do whatever science the astronomers at the University of California want to do. Currently, the instrument installed at the bottom of the telescope is called the CAST spectrograph. Now, a spectrograph is a device that takes the light from whatever you're looking at and spreads it out into all its component colors, just like a prism will take sunlight and make a rainbow. And we can look at the light from a star or a galaxy and figure out all sorts of things from its spectrum. Things like the color of the star will tell you its temperature, that hotter stars emit more blue light and cooler stars emit more red light. So red stars are cooler than blue stars. Also, when you look at that spectrum, you might see key colors of light are missing. And those missing colors are either emitted or absorbed by particular elements or molecules that the object is made of. And sometimes you'll see this particular fingerprint of colors that are missing or in excess, and you'll say, aha, there's hydrogen in that object, or there's nitrogen, or carbon monoxide. So that we can figure out from the spectrum what something is made of. Also, sometimes you'll see that characteristic fingerprint, but it'll be shifted a little bit to the red or a little bit to the blue. And that's what we call the Doppler shift. Now, we've all heard this effect with, say, ambulance sirens. As they come towards you, the pitch gets higher. As they go away, the pitch gets lower. Now, with light, similar things happen. As something is moving towards you, the light gets bluer. As it moves away from you, it gets redder. And so we can actually measure the speed of objects towards and away from us by looking at the spectrum. So that these instruments are very, very powerful. Now, some of the objects that we look at in the sky with this instrument currently are things like supernova explosions, so that we can measure how far away they are, what type of supernova they are. I myself do research on quasars and measure the redshift, so how fast they're moving away from us. And because of the expansion of the universe, if we know how fast it's moving away from us, we actually have a good estimate of how far away that quasar is as well. So tons of different types of research done with this instrument, and it's the most commonly used instrument. Now, another instrument we can put at the bottom of the telescope is called adaptive optics. Lick Observatory specializes in developing new high-tech instruments, such as adaptive optics. Our view through the telescopes is blurred because the Earth's atmosphere above us is turbulent, and we can correct it using technology. And so what we do is we use a laser that shoots out the telescope and illuminates sodium atoms above our heads in the mesosphere about 60 miles up, and it causes those sodium atoms to fluoresce, creating a fake star. We can then use that star to see how blurry it is and how it's being blurred. And we measure it up to 1,000 times per second. And then after we've measured the blurring, we then figure out what that turbulence was and put anti-turbulence on what's called a deformable mirror, which sits in the instrument at the bottom of the Shane telescope. That mirror can change its shape over 1,000 times a second to make nice, crystal clear images of the sky. So you can see this little example here, an uncorrected blur of a star, and then the corrected star is a nice pinpoint, so that we can get images sharper than the Hubble Space Telescope, because our Shane 3-meter diameter telescope has a bigger diameter than the Hubble Space Telescope. And of course, this is great technology to use for measuring the high detailed structures of a binary star, to see how close those two stars are together and track the orbits over time. Look for brown dwarfs next to the parent brighter star. I use it myself to look at the host galaxies around these bright quasar cores. So lots and lots of different research being done with this telescope. This console is the original console for controlling the telescope in the 1950s, when the Shane telescope was first used. Today, we don't use this console, it's all computerized, but if something fails with the computers, we still have a fully functional telescope with the telescope operator standing here in the dome, using all these dials and switches to move the telescope to where we want it to go to view the sky. So you can imagine back in the 1950s, the astronomer would be working at the telescope here in the dome, the telescope operator would be here, and they would be communicating with each other. And in the summer, it's nice and warm up here, but of course in the winter time, it would be very cold, and everyone would be bundled up in all the warm clothes they have, because you would be working all night in a cold dome. But it was worth it to get science on the second largest telescope in the world.
This is the Katzmann Automatic Imaging Telescope, and unlike the Shane telescope and more like our automated planet finder, this is a telescope which is robotic or automatic and dedicated to specific research interests. It's a very efficient telescope. So the idea is this monitors clusters of galaxies, looking for new point sources in those galaxies that are in the clusters themselves. And these are the exploding stars, the supernova, that can be followed up by their changes in brightness, and also by looking at their spectra and the chemistry going on in those environments. This telescope went into operation in the mid-1990s, and by virtue of that, it was at the forefront of technology developments in the era of robotic and remote and unsupervised observing. So it led the way in not only the robotic and mechanical operation of a telescope, but also in the queue and scheduling type programming for robotic and unsupervised observations. Some of the observations that this telescope and others made in the middle 90s contributed to our revision of how the universe works. So with data acquired by this telescope and others around the world, we were able to refine our understanding of these exploding stars, these supernovae, and the galaxies in which they were hosted. And this led us to the revelation that the universe was expanding, not as had been previously as assumed, as an ever-decreasing expansion, but we suddenly realized that the universe was expanding at an ever-accelerating rate. And this forced us to invoke a new force in physics we now call the dark energy, and is still an active area of study. And so this telescope still has a lot of work to do to assist in our investigations of that dark energy.
the frequent questions we get here at Lick Observatory is how do we handle earthquakes, since we are in California and that's a major hazard. And for the most part, Lick Observatory manages earthquakes with very little damage because we're on a huge mountain that's a big piece of bedrock, and it all moves very short jolts and usually doesn't roll, and that sort of rolling action causes most of the damage. That's not to say we haven't been affected by earthquakes. If you'll see the burned out building behind me, that is the historic home of Edward Emerson Barnard. Back in 1984, it was damaged by the Morgan Hill earthquake. Also, when we have earthquakes, it does tend to move the telescopes, but they're bolted to bedrock. So typically, after an earthquake, we will check the structure of the telescope and the domes, make sure everything is safe, repoint the telescope because the ground is moved, so you actually have to recalibrate the telescopes, and then go on with observing. So we've been very fortunate that earthquakes haven't affected Lick Observatory too extremely. However, back in the 1906 earthquake that was famous for destroying San Francisco and the massive fires afterwards, we had a seismograph here on site to record that earthquake, and it is visible in our visitor center, the original trace from that 1906 earthquake. Additionally, our astronomers, while they felt the earthquake here, there was not significant damage at Lick Observatory because it was sufficiently far away, but our 12-inch refractor in the north dome of our main building could point low enough so that they could actually view San Francisco and watch the fires evolving and changing in the city at the time. So terrible tragedy there, but the astronomers were able to keep tabs on what was going on in San Francisco. However, our major danger that surprises most people is wildfires here at Lick Observatory. We are on top of a mountaintop, and fires happen every year in California. It's part of the ecosystem. And so a number of fires have been on the observatory property, but nothing really threatened any of our buildings or caused major damage until August of 2020, when the SCU lightning complex of fires burned through Lick Observatory. And you can see some of the devastation it wrought behind me. Charred landscape. It actually burned what remained of the Barnard house after it was damaged in the 1984 earthquake. But we were fortunate in that our vegetation management and our marvelous firefighters from CAL FIRE and around the state were able to protect our telescopes so that all our telescopes were protected from the fire, and there was no damage from that.